Let's do just one more example. Again, we want to determine whether vector B is in the span of set V. That means that if B is in the span of set V, that means B can be written as a linear combination of the vectors in V. So that means there would be some scalars x1 and x2 and x3 and x4 such that x1 times the first vector plus x2 times the second vector plus x3 times the third vector plus x4 times the fourth vector. That this linear combination is equal to vector B. I can find these coefficients to make it work. Okay. Now we know that this is a different way to express a linear system of equations. So we can solve this linear system by finding the augmented matrix and getting it into reduced row echelon form. The coefficient matrix are the columns of my spanning set of vectors. So column 1 is vector 1, column 2 is vector 2, column 3 is vector 3, column 4 is vector 4. And the augmented part is the other side of the equal sign. What I want this linear combination to be equal to, vector B. Negative 15, 18, 12. Okay, we want to find the reduced row echelon form of this matrix. We could do it by hand, but we really don't want to. So let me quickly type this into our computer. So the computer can quickly do all the hard work for us. Okay. Okay. We have this pretty nasty expression. Okay, this nasty matrix, but it is a matrix, and we're happy the computer was able to do it for us instead of having to do it ourselves. Let's see what we get here. We're getting the reduced row echelon form of this matrix. We have first row is 1, 0, 0, 127 over 302, 525 over 302. Second row, 0, 1, 0, negative 9 over 151, negative 426 over 151. And in the final row, we have 0, 0, 1, negative 90 over 151, negative 183 over 151. Okay, we can go ahead and expand this now so we have room to work here. Okay, this last column is our augmented part. Let's first determine if we have a solution. So we don't have any rows that look like 0, 0, 0, 0, all on the left side of the augmented part and then 1 on the other side. Anything that looks like that. So we do have a solution, okay? In fact, the rank of this matrix is 3. We have 3 non-zero rows. Another way to look at it, I usually think about it in terms of my leading terms. I have 3 leading terms. A non-zero row has a leading term, so it's equivalent, okay? So I have 3 leading terms. The rank of the matrix is 3, but I have 4 columns. So I'm going to have a free variable, just 1, right? Because 4 is 1 larger than 3. The column that doesn't have a free variable is the last one in my coefficient matrix. So that will be the variable that I choose to be my free variable. Okay? Okay, so let's call this x1, x2, x3, x4 here. And let's start translating our solution. We've determined that we do have a solution. Okay. The equation has infinitely many solutions. And so before we even know what the solution is, we know that we can express vector b as a linear combination of our spanning set of vectors. We know we can choose x1, x2, x3, x4 to make this equation true. In fact, we're going to have infinitely many choices to make this equation true, okay, because we have infinitely many solutions. That means that vector b is in the span of V. So let's express B as a linear combination of the vectors in V. Okay? Okay. So let's work. It's usually best to work backwards when finding your solution. So I'm going to start with the last row, and already in the last row, I'm going to need that free variable. So let's start with the free variable. X4 is my free variable t. Okay? So the last row, I have 1x3 minus 90 over 151 x4 equals negative 183 over 151. So 1x3 minus 90 over 151 x4 equals negative 183 over 151. Okay, but we've decided to call x4 our free variable t. So instead of writing x4 here, I'm going to write t, so we know that's our free variable. Okay, solving for x3, I find that x3 is equal to 90 over 151t plus 183 over 151. And actually, I think I'll swap those around. I'll put the term without t first. So negative 183 over 151 plus 90 over 151t. Just personal preference. Putting the term with t second. Okay? Next equation. We're going to look at the second row of our augmented matrix, translate it into an equation. So that's going to be 1x2 minus 9 over 151 x4 minus 9 over 151 x4, but x4 is t, so I'm going to go ahead and plug that in, equals negative 426 over 151. So solve for x2, I get x2 is equal to negative 426 over 151. And then let's add the 9 over 151t to the other side of the equation. Okay? And finally, let's use our first row to get our first equation to figure out what x1 is. That's going to be 1x1 plus 127 over 302 is equal to 525 over 302. So 1x1 plus 127 over 302 x4. 127 over 302 x4. And instead of plugging x4, I will plug in our free variable t, since they're the same thing, is equal to 525 over 302. Okay, so let's solve for x1. So x1 is going to be 525 over 302 minus 127 over 302 t. Okay? So now I've expressed all of my x's, x1, x2, x3, x4, in terms of my free variable t, which means I can express the general solution to this system. 1, x2, x3, x4. The general solution to this system is going to be, so x1 is 525 over 302 minus 127 over 302t. x2 is negative 426 over 151 plus 9 over 151t. x3 is negative 183 over 151 plus 90 over 151t. And x4 is just t. If I break that into, for each component, the term without t in it, and the term with t in it, I get this. Okay? So any set of coefficients x1, x2, x3, x4 that can be expressed in this form for some value of t would solve the system. Okay? Would solve this equation, would mean that this linear combination is equal to this vector. Okay? Now the instructions here tell us to actually express B as a linear combination of the vectors in V. Now we have infinitely many ways to do that. Any choice for x1, x2, x3, x4 that satisfies this would work. Okay? But since I just need to choose one, I could choose whatever t I want and find one set of values for x1, x2, x3, x4 that will make it work. Okay? In this case, I don't want to add any nasty fractions together. Let's choose t equal to 0. And it is a choice. Again, any number t will work here. I could choose t to be 0. I could choose t to be 302. I could choose t to be negative 4,306,000,000. Okay? Any set of x1, x2, x3, x4 that has this form, using those as the coefficients to the linear combination equation will make the system work. Okay? So choosing t equals to 0. Let me just grab this so I don't have to write it all out again. So we got our linear combination equation. Okay, so what we're going to do, if I'm choosing t equals 0, then x1 would become 525 over 302, right? If t is 0, then this term would just go away. So x1 is 525 over 302. x2, again, I'm choosing t equals 0. So if t equals 0, x2 is just going to be negative 426 over 151. This term is just 0 times 9 over 151, which is just 0. So x2, with my particular choice of t, is negative 426 over 151. x3 is going to be negative 183 over 151 when t is 0. So negative 183 over 151. And x4, well, x4 is just 0 when t is 0. Okay, so this solves the linear system of equations. This is a linear combination of equations showing that we can express this vector as a linear combination of these other vectors. And I want to emphasize one more time, this is one way to do it. We have infinitely many ways to do it. This isn't even possibly the best way to do it. There's probably a cleaner way to do this. Maybe choose t equal to 1 and see what happens. Okay. If you choose t equals 1, you'll get different values for x1, x2, x3, x4. Those would also work as the coefficients to this. Okay, those would also show a way to find a linear combination of these vectors to equal to this vector.